Thank you, Tali. All yours.
Thank you, Ayush. So I'll just share my screen now. Okay, hi everyone. I have to say it's really weird to give a talk when I don't see anyone. So feel free to interrupt during the talk and ask questions, and let me feel that I'm not talking to a monitor. So the title of my talk today is Learning to Retime People in Video. And before I start, so just a bit about myself. This has been my career path so far. And as Ayush mentioned, I just joined the Weizmann Institute of Science as an assistant professor. My work is somewhere at the intersection of computer vision, computer graphics, and machine learning. And what I love most about working in this intersection is that it allows me to not only analyze our visual world, but also change it and enhance it by re-rendering images and videos. So today I'm going to talk about a line of work that is doing that, specifically by retiming people in videos. And what I mean by that is that we want to change the speed of frame. Sorry?
I think it was a random voice.
Okay. So basically, we want to change the speed of frames or the speed of individual people within frames in order to enhance the way we perceive video content. And we can see such retiming effects, advanced effects in films all the time. So for example, slow-mo or fast motion or a combination of them. They are often used to focus the viewer on specific events or actions in a video. But of course, in films, to produce such effects, we need special cameras and lots of staging. So today I'm going to talk about how retiming effects can be achieved in everyday videos as a post-process. And I'm not sure how you're gonna, how you're seeing these videos, but I'm pretty sure they're not gonna stream that well. I'm gonna play lots of videos. So I'm gonna put my presentation online. So please, if you can, check out those videos later offline. Okay, and also just to give a bit of context, people in videos is something I've been recently quite interested in. I looked into different aspects of analyzing and visualizing people's geometry and motion. So for example, in this work from WIST 18, we take just an ordinary video of this Olympic runner, and we turned it into what we named a motion sculpture. It's a 3D visualization of the structure that is swept by the runner as he moves in space. And because it's 3D, it provides much more information about shape and motion than what's available to us in the original 2D video. You can also 3D print a motion sculpture and explore it from any viewpoint that you want. And this work is also presented in a new exhibition in the MIT Museum. It is now closed because of COVID, but I hope it will be reopened again. In CVPR 19, we basically predict dense depth map for every frame in a video in cases where both the camera and the people in the scene are naturally moving. And in this case, a epipolar geometry constraint break, and we cannot estimate 3D just using triangulation. So instead, we took a data-driven approach. We found this surprisingly useful data on YouTube. These are many videos that are named mannequin challenge videos. These are videos where people freeze in some natural pose, and there is a camera touring the scene and capturing them. And because everything is static, including the people, you can apply structure for motion and multi-view stereo algorithm to compute depth. So we use this depth to supervise our depth prediction model, which allowed us to get state-of-the-art results in this challenging case. And again, feel free to stop me at any point, please. So for the rest of this talk, I'm going to talk about two more recent works, SpeedNet and layered neural rendering. And it's a lot of content, so I apologize in advance if I'm gonna, refer you to the paper for some technical details. So I'm gonna start with SpeedNet, and the motivation for this work is watching video content faster. We are all watching more and more videos. Each minute, over 500 hours of video are uploaded to YouTube alone. So it seems necessary to be able to watch video content more efficiently. So in fact, in YouTube, there is an option, like you can speed up a video, but it is done very naively just by uniformly dropping frames. So this is what you get if you speed up a video by 2x using YouTube. And you can see it results in very jittery and unnatural motions. So our idea was, okay, let's adaptively speed up the video. Let's analyze the video content and compute a time-varying speed-up curve that you can see below here. And if we do that, this is the result you get. And I hope you can see it, but our result has the same duration as the uniformly sped up video, but it's much more naturally looking. And of course, the key question is how to decide how much we can speed up each segment of the video. And you can start thinking, about handcrafting some features based on motions and so on. We wanted to approach this problem from a more general perspective. So when we humans watch people moving in a video, we can easily tell their speediness. What I mean by speediness is that we can tell if they're moving at their normal speed or slower than normal speed or faster than normal speed. Why we can do that? We simply watch people move in the world, and we have prior knowledge about their natural rate of motion. So in this work, we want to predict speediness in videos automatically. Once we have such a model, we can use its predictions to adaptively speed up a video and for other applications, as I'll show later in the talk. So how this was done, we want to predict if an object moves faster at or slower than their natural speed. And as a proxy to this task, we trained a network that we named SpeedNet to classify if a given video clip is of normal speed or sped up. So this binary classification task is easier and simpler to train than a regression network. And we can train it on many, many examples in a self-supervised manner without requiring any manual labels. So if you're familiar with learning and using the arrow of time work, it is a task that's related to to SpeedNet. In their work, what they are trying to do is to train a model they train a model to predict if a given video clip is played forward or backward in time. Here, our goal is not to learn the direction of motion, but rather we want to learn properties about the magnitude of motion in the real world. And the main challenge in basically training such a network, in the beginning, we thought, wow, this is simple and we have so many examples, so, what's the problem? But it turns out to be really challenging. And the reason for that is that the network can easily cheat. It can pick up all sorts of signals that are unrelated to real properties of natural motion. So for example, when we generate the sped up examples, we introduce aliasing in time. And this aliasing can be picked up by the network to determine if a segment is sped up or not, while ignoring basically all the motions in the scene. And we worked pretty hard to avoid such cheats. And please check out the paper for more details. We have like a dedicated augmentation, data augmentation scheme and training regime to handle that. Okay, so I'll go a bit into the network architecture. Our input is 30-frame video segment, which is first fed into a 3D conv network. This network is largely based on a state-of-the-art action recognition model. And this model learns space-time features, where you can see here, the spatial dimension is reduced by a factor of 32, and the temporal dimension is preserved. We then collapse the spatial and temporal dimension into this 1K feature vector by pooling. We apply spatial max pooling and temporal average pooling. Finally, we reduce it into this binary output using a single conv layer. And we train this using binary cross-entropy loss. So what happens at inference time, we can run our model in a sliding window fashion on a video clip. So we now get a prediction for every frame in the video, and what I'm visualizing here are the logits. Okay, so now that we have SpeedNet's predictions, we can use them to adaptively speed up a video. So the intuition is as follows. We can basically keep speeding up a video segment as long as SpeedNet thinks it is not sped up. Again, I'm skipping some technical details here, but we have a good all optimization framework to estimate a temporally varying speed up curve. The speed up curve has to kind of like smoothly change in time, but it also has to meet the total desired speed up factor provided by the user. So if the user said they wanted 2x, then this curve needs to provide the total 2x speed up. So let's see how it works. On the left, we have a video that was uniformly sped up by 2x. So the duration is half of the original duration of the video. And on the right, we use the adaptive speedup instead. So again, we get a video that has the same duration, but I hope you can see it's much more naturally looking. Here it is again. We also performed the user study, which showed that users preferred our adaptive speedup in all cases. Okay, so when you think about speediness, there is a built-in correlation between the magnitude of motion and speediness. Basically, you know, when we create our sped up examples, by construction, we basically cause the optical flow to be larger on the sped up examples. So we wanted to evaluate if and to which extent SpeedNet goes beyond this simple baseline. We have numerical evaluation in the papers that shows that SpeedNet is superior to a flow baseline, but here is just a visual example that demonstrate this. So here we have a video. You have a person walking far from the camera, then he goes out of the frame, and then he come and walk closer to the camera. So if you look on the magnitude of the optical flow, this is how it looks like. You get, you know, larger magnitudes of flow when the person is coming closer to the camera. And here is our, you know, speediness predictions, and you can see that SpeedNet predicts normal speed for the entire video, regardless of the magnitude of motion. If we input to SpeedNet the video played at twice the speed, this is what we get. So you can see that in the walking segments, they do indeed get recognized as faster than normal human motions, whereas the static segments where we don't have motion or very little motion, they are getting classified as normal speed. So by learning to predict SpeedNet can learn this powerful space-time representation, and we can use this representation for other tasks as well. For example, we took our pre-trained SpeedNet and then we fine-tuned it for action recognition. And our model was able to beat all other models that were pre-trained in a self-supervised manner on Kinetics. We can also use our model for video retrieval. So we extract the SpeedNet embedding for a query clip. And then we can look for nearest neighbors in the embedding space. And we can do that within the same video. So here you can see the retrieve top 3 results from the same video, or across videos over a data set. And I guess it's important to note that SpeedNet was not trained specifically for action recognition, so many of these nearest neighbors are not of the same class, but they contain similar motion patterns. So you can see that the person free falling from the sky has similar motion to the person surfing in this example. Okay, we can also use SpeedNet to detect speediness in both space and time. So this is an artistic video that was made by slowing down only certain regions in the video. I don't know if you can see, but the people on the right are slowed down. So, and here I'm showing a visualization of SpeedNet's prediction using class activation maps. And you can see blue or green regions are normal speed and yellow-orange regions are slowed down. And you can see how, you know, the regions are correctly detected. Okay, I feel I'm speaking very quickly, and I'm in this black hole. So I would like to stop and ask if there are any questions.
Only one question. So it seems to me that right now SpeedNet is kind of dissecting it into two parts, like foreground and the background. But if there are multiple motion modes in a video, it might be challenging to learn a suitable representation on it. So let's say the people in queue were moving like almost like in one pattern, and stationary thing was happening in a similar way. But there was one person moving fast. But let's say if I add a third person or a fourth person, or say dancers in that video, then the speed of people doing things would be very different, and there would be multiple modes in just one video. Whereas
That's
all
true.
the training examples that so far have is generally say one person doing an activity in a background, which is generally
Yes.
stationary.
Yes. We trained the model on Kinetics, so you do get like pretty complex, scenes there. If you take a closer look on the architecture, you would see that, when we collapse the spatial and temporal dimension, what we are doing, we are taking max pulling on the spatial dimension and average pulling on the temporal dimension. So the average pulling on the temporal dimension is supposed to kind of like avoid very spiky motion. Let's say you just have like very spiky motion. You don't want to throw the model towards predicting that the video is sped up. And the spatial kind of like pulling on the average pulling on this, the max pulling on the average on the spatial domain kind of like lets you aggregate information, from different objects. We didn't carefully did analysis of what happens in this case where you have multiple modes of motions, but I would expect it to kind of like aggregate this information in a sensible way. It will be interesting to look at this more carefully.
Right. Are there other questions? People can unmute themselves.
Okay.
We can move
So
forward.
I'll move forward. So in SpeedNet, I basically showed how can we, change the speed of frames. Now I'm going to talk about how can we change the speed of individual people within frames. So this work is accepted to SIGGRAPH Asia and will be presented there pretty soon. And the motivation for this work is basically making videos more artistic, engaging, and fun. So what you are seeing here is just like a snapshot of my own personal video collection. Most of my videos are of my kids, obviously, and I take many of them. But even for me, these videos are pretty boring, pretty often. So we wanted to make them less boring. And we want to do this by changing the speed of individual people within frames. So let's see an example. This is a video where we told the kids to jump together to the pool. But of course, each child jumps at a different time. And as you know, making kids do what you want is an impossible task. So instead, it's easier to just retime them computationally. So I'm going to show you the result. Here is our retimed result. All the children jump together, and it's done in post-processing. And you can notice how not only the children are retimed, but also all the water splashes, reflections, all the scene elements that are related to them, they're just following them properly. So really capturing these complicated space-time correlations between people and all these time-varying scene elements, this is the key for producing realistic retiming effects. So take a look at this video. If I want to do any retiming of the people in this scene, we also have to retime the reflection on the glass as well. Otherwise, the result won't look realistic. Another challenge is that retiming individual people will often create disocclusions in the scene. Like, for example, here, the person in the background is occluded in the original video, but when I retime the foreground person, this region will be revealed, and we must realistically synthesize them in order to create a realistic effect. Okay, so the way we handle that and tackle these two big challenges is by decomposing the video into layers. These layers are human specific. What I mean by that is that each layer is associated with the person in the video, but it not only contains the person, but also all the scene elements that are related to them. So here you can see again the reflection on the glass in each of the person's layers. We also have a background layer, as you can see here. And another key feature of our decomposition is that it provides a full body estimate of the person in each layer. So even if the person is occluded in the original frame, it will be fully reconstructed in their layers. And if we have these estimated layers in hand, we can now edit the video by simple manipulation of the layers. So for example, we can just remove a person from the video by simply not rendering their layers, as you can see on the right here. And of course, the task of decomposing a video into layers, it's not new. The pioneering work by Wang and Edelson inspired a great body of follow-up work. Recent methods, of course, use the power of deep learning, like the stereo magnification work, where they basically take a pair of an input stereo pair of images, and they train a model to predict layers that corresponds to physically accurate depth. And their goal is to synthesize new views of a static scene. We also use the power of deep learning, but in our case, our layers are not meant to be strictly accurate in terms of depth. In our case, the layers, again, correspond to a person in the video, along with all the correlated effects. And our model is trained only on the input video without observing any additional example. It is trained in a self-supervised manner without any labels. And we named our technique layered neural rendering because it combines classical elements from a graphics pipeline. It was greatly inspired by the deferred neural rendering work. They also trained their neural render on a single video. And I'll just briefly kind of like go through their method. They represent the geometry in each frame with a UV map. So typically in graphics, you have the UV map and you have like an RGB texture map. And to render an image, you use the UV map to sample the texture, and that's how you render a frame. Here, they replace the RGB texture with a trainable deep texture map. So the sample texture is now, a latent representation, and it is passed through a neural renderer, and then this neural renderer decodes it into an RGB image. It is trained to reconstruct the original video frames that way. And they use this trained model to do novel view synthesis, edit the original scene, remove duplicate objects, and so on. I think the key thing to notice here is that it allowed them to work with imperfect geometries. Like this UV map doesn't have to be perfect, but still you will be able to reconstruct reliably the output image. Okay, so in our case, we represent the appearance of each person in the video with a deep texture map, and the geometry in each frame with a per frame UV map. We also represent the background. It has its own deep texture and its own UV map. And in the case of a static camera, this background UV is just like an XY coordinate grid for all the frames. We then append the background's UV behind each person's UV map, like you can see in this visualization. And we use this UV map to sample the textures. The sample textures are basically the input to our neural renderer, and each one of them represents a layer. We feed each of these sample texture in a separate forward pass into the neural renderer. And again, the task of this neural renderer is to output a color image and an opacity map for the corresponding layer. So after we predict all the layers, we compose them back using standard back-to-front compositing. We assume that we know the depth ordering between the layers. And if we do that, we get back the original frame. So we apply several losses to train our model. The first is, of course, reconstruction loss. We want the layers, when we put them back together, to reconstruct the original frames. We also have a regularization loss that we apply on the alpha mat. Basically, we want the alpha mat to be sparse. So this loss is a combination of an L1 and an L0 loss on the alpha mat. And these two losses alone are not enough to allow the network, the optimization, to converge from a random initialization. So we also have to bootstrap and initialize the network, and we do that by first computing, a rough foreground mask for each person in the video, and then we encourage each learned alpha mat to match the person segments that is associated with their layers. We turn off this initialization loss after a few epochs and let the alpha and let the optimization kind of like change the alpha mat and the layers. Okay, so we trained this our neural renderer on the entire video. And now I want to explain a bit about the intuition. You can see that at each fourth pass, the neural renderer sees only an explicit representation of a person over a static background. But in order to accurately reconstruct the full video, it must also reconstruct all the time-varying scene elements, like the reflection on the glass. So it is forced to place these details in some layers. It is forced to kind of like, estimate those deltas and just, pick a layer and put them in that layer. But why does it manage to pick the right layer? Why does it manage to, place the reflection with the person causing it? That's like a question that we asked ourselves. And in the next few minutes, I'm going to try to give you some intuition about why it works through several toy examples. So here we have just a person walking over a static background. And as I mentioned, we initialize the network using this rough foreground mask. And starting from this initialization for the alpha mat, the network is trained over many epochs to refine these results. So you can see here the training progression. And you can see that, as we go and train the network further, details that are not represented by the initial mask are learned. So you can see that in the beginning, we get a little bit of colors, then we add some details, then the hair and the loose clothing and the shoes are being reconstructed. So now let's get more complicated. Here we added two green squares. One is smoothly following the person, and the other is randomly moving. And now let's see how training behaves and what types of effects get reconstructed more quickly. So as you can see here, the person is first reconstructed, then the square that is correlated with the person. And only after many epochs, the random square is being reconstructed. So we can observe that correlated motion is learned earlier than uncorrelated motion. In this example, we have two squares that they are both moving along with the person, but one is closer to the person than the other. And we can see here again that the person is being reconstructed, then the closer square, and then finally the more distant one. So similarly, nearby effects are learned earlier than distant effects. And now if we have two people, each moving with their own square, we assign a layer for each person using these rough trimaps. And here too, first the people are learned, then each person's layers kind of like grabs the most correlated elements in space or in time. So the squares are assigned to the right layers. And this finding is closely related to the deep image prior work, where they basically show that if you take a CNN and you train it from scratch to kind of like reconstruct or overfit to an image, the structure of the CNN gives bias towards outputting natural images. So it basically takes fewer training iterations to reconstruct a natural image in which patches are correlated and more coherent than a random noise image. So in a similar manner, because we are training over a video, the effects that are closely correlated with the person in space or in time or both are learned more quickly than other effects. So if we take a look on a layer, the other effect with respect to a person layer behaves like noise, and they take longer for the network to fit. So let's see another example. Here we used our predicted layers to freeze in time one of the couples. So this is a super challenging scene. You have loose clothing, complex motions, and you can see that during the freezing effect, reflections, shadows are all nicely preserved. So the quality of our layer decomposition depends on having reasonable input UV maps. And the problem is that, existing methods like dense-pose, they make pretty bad errors, like dropping an entire body part when there are occlusions between people, especially when there are occlusions between people. So we cannot use them directly. Another problem with dense pose is that it only provides UVs in the visible regions. But again, we want to get, if we're going to use this, like these incomplete UV maps, we're going to get incomplete layers with artifacts. And for retiming, again, it is crucial to have complete UV maps for all layers in the presence of occlusions. So we want to have a method that can produce complete and stable UV maps, even when we have occlusion. So our solution is to first go through key points. And the reason for that is that key points tend to be much more robust, and they are easier to edit. We can interpolate key points. We can manually correct key points. They are much more friendly to us to work with than a dense UV map. So we first extract key points. We can filter, edit, or do whatever we want with them. And then we trained a network that converts the key points into a full body UVs. We trained this offline. We have kind of like a model that was trained specifically for this task. We used videos, very clean videos of just like a single person walking. And we used alpha pose and dense pose to get like pseudo ground truth and train this model for this task. And now if we used our full body UVs, this is the result we get, and the predicted layers are complete and of higher quality.
Tali, one quick question.
Yes.
Why didn't, it's possible that the UV map predictor, dense pose, or key point predictor can also pick the reflected version as a real, say, it can consider that it's a real human being and can also predict dense pose over there, right?
Are you asking if dense pose kind of like assigns UV map for the shadow region, for example?
Yeah.
Oh, it was not trained for this task. The UV maps are basically, there are 2D coordinates that map to a kind of like a template mesh of a person. So they're not designed to capture any, effects that are not humans. I haven't seen dense pose capturing shadowed regions or, things in the background. Their failure mode is mostly losing body parts or, having incomplete UV map.
I see.
Yeah. Okay, so here we can see kind of like, the full breakdown of the layer decomposition results. In this example, because of self-occlusions, we grouped each couple into a different layer. So layer 1 has one couple and layer 2 has the other couple. And things to notice here is that you can see that although the trimaps are pretty rough, they don't contain the clothing, they don't contain like the fine details, our alpha mats do. And they managed to kind of like refine the initial initialization significantly. And again, you can see all the, the scene, the time varying scene elements in the layers. You can also see kind of like, a limitation of our approach where you see this flickering light in layer 2 output. You can see, again, these are flickering light that they don't have to do with the people, not the first couple or the second couple, but they are forced to be placed in one of the layers. So they found themselves in layer 2 here, which is having a dynamic background layer is still something to be explored. Okay, so let's see another example on a real video. Here we have many people moving and jumping, causing complex deformations, casting shadows. And our method produces a layer for each person that include only the deformation effects caused by that person. And now we can use the key points to automatically align each person's jumping time. So I'll show before temporal alignment here. And after temporal alignment. You can see they're all jumping, they're all in the air at the same time, they're all touching the trampolines at the same time, and everything looks realistic.
So I don't know, maybe you're gonna talk about it later, but let's say since my input is dense pose, like UV map for a person, can I also, let's say, change the UV map, provide some other UV map so that I can change the activity of the person in the video?
Right, so this is a good question. So, you know, there are many methods right now, you know, like everybody dance now. Can we do everybody dance now? We are not, the method is not designed to basically create new poses or generate new poses. It is very much kind of like overfitted to the poses it observed during training. It won't be able to generalize well to new poses. For retiming, you don't need to generalize.
Right.
All the retiming effects that we are, you know, that I'm showing here are simply produced by just changing the timing of the output layers. So you predict the layers once, and then you can compose them in any order that you want. You can do warping in time and so on, but you are not changing the predicted layers themselves.
Right. I think that makes a lot of sense with the flowing dresses as well, right? That's how it's able to learn the flowing dresses nicely.
Yes, yes. I mean, it's a big. I think it's a great research question of how to make you know, neural rendering, like the deferred neural rendering approach, or this approach, kind of like also generalized. But I think, you know, what we are seeing here is the deep image prior property of this model is tightly related to the fact that it managed to memorize or kind of like overfit to that one input video.
Right.
Yes. Okay, so here's another fairly complicated example. We have a bunch of kids running towards the camera, and we can use our method to slow down all the kids except one. And here also the depth ordering changes over time. This is the result. Here's an example where the background is not static, and we can preserve the original camera motion. I know I didn't explain exactly how do we do that. I'll just first show the result. So here we kind of like retimed and also duplicated the girl. So just kind of like in a high level, you can think of the background as kind of like an extended image, like a panorama where each frame kind of like sample only the visible part. In practice, we kind of like register all the frames in the video into this common coordinate system, and then we apply homography to the background's UVs for each frame. And that's how we manage to preserve the original camera motion. Yeah, so I have to say this is not a fast method. The total running time on 2 GPUs for our videos ranges from 5 to 12 hours, depending on the video length and the numbers of layers. There are two ways that we can speed it up. First is kind of like to develop, a feed-forward model, like people have done in the style transfer. For style transfer, where they started from optimization method and then they kind of like moved away from that and trained the feed-forward network to do that. I think it will require a lot of thinking about how to do that and how to get these correlation effects to to be captured in a feed-forward fashion, but it's definitely an interesting future direction. We can also, take a brute force approach and just throw it on many TPUs and hope that, we can just parallelize it and get it to train in, orders of magnitude faster. Do I still have time?
Yep.
Or are we in a rush?
We have 10-15 minutes.
Oh, okay. So that's plenty of time. So I'm going to show a few more things. Again, I might have problem with this slide, but I also want to mention that, it's not always perfectly working. So here, if you remember the splash, the kids jumping in the pool example, I want to show you what happens sometimes. Oh, this bluish thing is, I don't know, it's an artifact, but what I'm showing here is the Trimap, and I hope that you can see that this Trimap is completely wrong when the kids on the left here, it jumps into the pool. And that kind of like creates an error. It basically, the splashes of that kid appears in that second layer, and they shouldn't. But we can address this by, simply editing the Trimap. So you can see here the edited Trimap. You see the splash here. So we only labeled like one frame and propagated it into a segment. But now that we've done that and we bootstrap the network, telling it this region should appear in that layer, then it managed to get rid of this artifact. So there is also definitely, room for user interaction in some of the very complicated scenes that I've showed here. And I think that, yes, this we covered. Yeah, so I think that's the end of my talk. And I'd be happy to take questions or comments.
Okay, people can unmute themselves, ask question. We have time for questions.
Maybe I can stop sharing screen so I can see people, or?
People are generally, the cameras are generally turned off, which I don't know why, but that's the usual scenario. Okay, maybe I'll start with the question. For the first part, so you use, let's say, the video representation for UCF 101 and HMDB dataset, while the, let's say, the initial
for
model
the action recognition.
Say it again.
For the action recognition, you mean?
For action recognition.
Yes.
Now, is it also possible to use that for kinetics?
No, we use it for kinetics. The numbers that I've shown here are on kinetics. Wait, sorry.
Wait, these are UCF 101 and HMDB.
Yes, I think we also have the numbers for kinetics. No, wait, this is we use kinetics, but I think the evaluation was done on these data sets. I'm not sure why we.
Right. Yeah, that's what my question was. Like, did you try on kinetics localization or recognition things as well?
To evaluate on kinetics, kind of like action, to get numbers on how accurate the. I think we looked on this because these data sets were, what was commonly used in the self-supervised methods. I don't think we computed the numbers on kinetics, but maybe I'm not remembering correctly. I should check.
Right. And for the second part about when you're rendering people, is there some other proxy to dense pose that I can utilize such that I can also go beyond retiming people? So let's say there are a lot of videos of, say, birds, there are a lot of videos of cats and dogs, but instead of having an explicit UV map for, let's say, person that we have in the current framework, is there some latent representation that I can have for a category? So I just define a mask over there, and then I say that learn a latent representation for this particular category and be able to retime it.
Yes. Yes, the answer is yes. These are current directions that we're working on. You know, going beyond people. You know, being able to kind of like map out general objects. So the answer is yes. I'm sorry that I'm not giving any further detail. Yeah.
Yeah. Okay, so someone is there. Tom, you have a question?
Had a comment or a question. I was wondering if like you considered any ethical implications or ways to detect like some of these video altering methods, because I remember like a couple years ago there was a video that was like, or at least there's a lot of research in like detecting deep fakes, and then there was a video of like Jim Acosta, like where it looked like he was karate chopping someone, but it was just like a couple frames that were removed. And so do you guys or does your team also like consider detecting methods where videos are altered?
We haven't looked in this direction at all. I think we were mostly kind of like, you know, fascinated by this ability to decompose the video in terms of, you know, technical. I'm trying to think, you know, if there is a way to use this decomposition to kind of like pick up, you know, deep fakes, but I don't have like an immediate direction that I can point out. It will be interesting. I don't know if those deep fakes, are you talking about deep fakes that were produced just by retiming videos or by other means?
It could be anything, I think. Like there's a lot of like GAN detection, but I guess these time altering methods could also be considered a deep fake, maybe.
So one place I can tell is, okay, I get this question as well a lot of time. So one place where I can tell, actually two incidents that has happened. One is in the White House Correspondent, where there was an intern and somebody just increased the frame rate so that she looked aggressive, and then there was all the mess on social media. And then there was another case of Nancy Pelosi, where somebody reduced the frame rate and she looked a bit drowsy in the video. And that also got viral on social media. So I think he's asking on that front, like, is there some way also that if there is a video, this is the question I also get, if there is a video that has been manipulated, so that whenever it is uploaded on something like social media, can we say that it's a generated content or is it a realistic content?
So my answer is, I think that, you know, so these methods are obviously not designed for this task, but I think that, you know, for specific use cases, if you're looking for a, kind of like a generic algorithm for deepfakes, this is not the case. But if maybe for specific cases, like I showed these visualizations on this artistic video for SpeedNet, I don't know if you recall, like this video, right, where we had like, you know, this video has been altered, like the people on the side here are slowed down, and we were able to kind of like detect this or visualize it, you know. So I think for specific cases you could make use of it, but it will require some thoughts of, you know, I don't know how to scale it to a more generic algorithm that could detect any type of deepfake in videos.
Right.
Great, thanks.
Sure.
The questions, we have time for 2-3 questions, I think. Okay, if not anyone, then maybe I'll ask. Okay, you can go for it.
Hi, I'm wondering will the record of this seminar be posted somewhere that I can see?
Sorry, I couldn't
the first part.
Then we cannot hear you properly.
I'm sorry?
You'll have to repeat yourself. We didn't get the question.
I'm sorry, my network is not so good. Sorry.
Try now.
Sorry, my network is not so good. So. Yeah, my question is, will the record of this seminar be posted somewhere so that I can see later? Since my network is not so good, so I want to review it again.
I think.
Oh,
yeah.
Yes, I think the talk is recorded, right? And I hope to put the slides on my website. So because the videos are not streaming well, so you know, you would be able to just download the slide deck and watch it offline. At least the videos.
Thank you.
Okay. So, Tali, my last question, maybe perhaps. So, in the case of moving cameras, basically, let's say, so for stationary cameras, background estimation is okay. I understand you can just take average, something would work up. But in case of say moving cameras, things can be really tricky. And also, like there's a big scope of things that one can do with moving cameras at test time. Let's say, like what camera pose should I consider in generation, right? So for example, right now you consider at test time, you consider stationary camera. Can we also?
We preserved the original camera motion and then we freezed it.
Yeah. Is it also possible to preserve the camera motion and then retime it?
Preserve. I think it should be possible. Yes, like what we did. So what we did for the background is pretty kind of like, you know, simple in the sense that if you can align the background pretty well with homographies, then what we did would work well. Otherwise, you need some fancier algorithm, like, you know, estimate the 3D structure of the scene and have a representation that takes into account, you know, parallax, 3D parallax in the background that could occur. We kind of like simplified this in our version and only applied homographies. Yeah, but I think in order to kind of like take you know, a more careful treat in the background, you have to take into account 3D geometry and parallax effects and so on. It kind of like related to the stereo magnification work in some sense.
Right. Yeah, no, I agree. That's right. All right. Are there other questions people want to ask? I think people are not asking question today. Maybe if not, then let's thank the speaker. Thanks, Tali, once again.
Thanks for having me. See you. Bye-bye.
Bye.